Let us discuss the solution of question number 69, in which we need to find the smallest degree of the polynomial that interpolates the given data. So to solve this question, we use Newton's divided difference interpolation. So for that, we need to construct the divided difference table for the given data. As you can see, the x values are given to us and the corresponding function values are also given to us. The x values are 0, 1, 2 and 3 and the corresponding function values are 4, 5, 8 and 13. Usually we denote the x values by x0, x1 and x2 and so on, and similarly we use f0, f1, f2 and so on to denote the function values. So as you can see here, our first value is 0 for x, so we use x0 to denote that. So x0 equal to 0, x1 equal to 1, x2 equal to 2 and x3 equal to 3. Similarly, we have f0 means the corresponding function value, that is f of 0. So f0 is 4, f1 is 5, f2 is 8 and f3 is 13. Now we are going to calculate the first order divided differences using the data values. So if we use the data values x0, f0, x1, f1, the first order divided difference is defined by f1 minus f0 divided by x1 minus x0. So f1 minus f0 means 5 minus 4 divided by x1 minus x0, that is 1 minus 0. So we get 1. Similarly, the first order divided difference using the data values x1, f1 and x2, f2 is defined by f2 minus f1 by x2 minus x1. So it is 8 minus 5 divided by 2 minus 1, so it is 3. Similarly, the other first order divided difference we calculate using the data values x2, f2 and x3, f3, which is defined by f3 minus f2 divided by x3 minus x2. So f3 minus f2, that is 13 minus 8 divided by x3 minus x2, that is 3 minus 2, so which is 5. So after calculating all the first order divided differences for the given data, now we use these first order divided differences to calculate the second order divided differences. The second order divided difference using the data values x0, f0, x1, f1 and x2, f2 can be calculated using the first two first order divided differences. So it is 3 minus 1 divided by x2 minus x0, that is 2 minus 0, so which is 1. Similarly, the second order divided difference using the data values x1, f1, x2, f2 and x3, f3 is calculated using the first order divided differences here, f of x1, x2 and f of x2, x3, which is 5 minus 3 divided by x3 minus x1. x3 is 3 and x1 is 1. So here 5 minus 3 divided by 3 minus 1. So we have 1. As you can see here, all the second order divided differences are equal. So the third order divided difference is 0. If you calculate using the formula, you can see 1 minus 1 is 0 divided by x3 minus x0, which is 3. So ultimately we will get 0. Since the third order divided difference is 0, so the given data represent a second degree polynomial. So option C is correct. If you want to find the polynomial using the Newton's divided difference interpolation, then you use this formula. And if you substitute the values, the polynomial is p of x equal to x square plus 4. In question number 70, we have to find the second order Newton's divided difference of the function f of x equal to x square at the points x0, x1 and x2. Use a shortcut trick here. You can see the function is a polynomial of degree 2. So when we find the second order Newton's divided difference for a polynomial of degree 2, it is nothing but the leading coefficient of the polynomial. So here the leading coefficient of the polynomial is 1. So the second order Newton's divided difference of the given function is 1. So option B is correct. Alternatively, we have to construct the divided difference table for the given data. So as usual, we write the x values vertically. So here the x values are x0, x1 and x2. Then we write the function values, corresponding function values here. f0 means f of x0. So you know that f of x is given, it is x square. So f of x0 is x0 square. Similarly, f of x1 is x1 square. So f of x2 means f2, which is x2 square. Now we have to calculate the first order divided differences. So the first order divided difference using the data values x0, f0 and x1, f1, it is defined by f1 minus f0 by x1 minus x0. So f1 means here f of x1, which is x1 square, minus f0. f1 minus f0, that is x1 square minus x0 square, whole divided by x1 minus x0. So we get here x1 plus x0. Next, we calculate the other first order divided difference using the data values x1 f1 and x2 f2, which is f2 minus f1 divided by x2 minus x1. So f2 is x2 square minus f1 is x1 square and whole divided by x2 minus x1. So ultimately we get x2 plus x1. Now let us calculate the second order divided difference using the first order divided differences. So the second order divided difference using the data values x0, f0, x1, f1 and x2, f2 can be calculated using the first order divided differences, that is here x2 plus x1 minus x1 plus x0 whole divided by x2 minus x0. So you can see here, if we calculate this, finally we get 1. So option B is the correct option. Also remember that the nth order Newton's divided difference of a polynomial of degree n is equal to the leading coefficient of the polynomial, that is the coefficient of the term with the highest power or degree. In question number 71, we need to find the error when the given integral is approximated by trapezoidal rule. So as you can see, to find the error, we need to calculate the true value and the approximate value of the given integral. To find the approximate value, use the trapezoidal rule, but to find the true value, we need to know the function p of x explicitly. But you can see here, the polynomial or the function p of x is not given to us explicitly, but the values of the polynomial are given at a set of distinct points. So first of all, we have to construct the polynomial. So we can use any interpolation here. So let us use Newton's divided difference interpolation. So for that, we have to construct the Newton's divided difference table. So you know the x values are 0, 1, 2, the function values are 1, 4 and 15. As usual, let us write x values vertically, x0 equal to 0, x1 equal to 1 and x2 equal to 2. And then we write the function values p of x. So p0 or f0, here in p0 you write. So p0 is 1, p1 is 4 and p2 is 15. Let us first calculate the first order divided differences. So p1 minus p0 by x1 minus x0, that is 4 minus 1 by 1 minus 0, which is 3. Next 15 minus 4, that is p2 minus p1 divided by x2 minus x1. So it is 15 minus 4 by 2 minus 1, which is 11. Next, using these two first order divided differences, we calculate the second order divided difference, 11 minus 3 divided by x2 minus x0, that is 4. So now using Newton's divided difference interpolating polynomial formula, we obtain the polynomial p of x, which is equal to 4x square minus x plus 1. Now to find the true value of the integral, that is integration of p of x with the limits 0 and 2, we integrate 4x square minus x plus 1. So ultimately we obtain 32 by 3. Next we have to calculate the approximate value of the integral. So to do that, we use trapezoidal rule. So here you can see we have 3 points, x0 equal to 0, x1 equal to 1 and x2 equal to 2, and the points are uniformly distributed with step size h equal to 1. You can see x1 minus x0 is 1, also x2 minus x1 is 1. So the step size h is equal to 1. Now using 3 points, the trapezoidal rule basically is given by, here we have 3 points, so we have 2 subintervals. So we can use the composite trapezoidal rule, which is h by 2 into p of x0 plus 2 times p of x1 plus p of x2. Now we substitute the values here. So h is 1, so 1 by 2, you can see here we have already calculated the value. So 1 by 2 whole into p of x0. P of x0 means p of 0. Here it is 1 by 2 p of 0 plus 2 into p of x1. x1 is 1, so p of 1 plus p of x2, it is p of 2. Now we use the values p of 0 is 1, p of 1 is 4 and p of 2 is 15. So using the given values of the polynomial p at x equal to 0, 1 and 2, we obtain the approximate value of the integral by trapezoidal rule, which is 12. Now the error is true value minus approximate value, so which is 32 by 3 minus 12, which is minus 4 by 3. So option C is correct. In question number 72, an initial value problem is given to us. We have to find the value of y at 1.1 using Euler's method with the step size h equal to 0.1. The given differential equation is derivative of y equal to x plus y with the initial condition y of 0 equal to 1. You have to find y at 1.1 using Euler's method. So Euler's method is given by yn plus 1 equal to yn plus h into f of xn comma y. So if we compare the given differential equation with the standard form, that is derivative of y equal to f of xy, then here you can see f of xy is x plus y. From the given initial condition, we have y of 0 equal to 1. So we take x0 equal to 0 and we have the step size h equal to 0.1. So x1 is x0 plus h, which is 0 plus 0.1, which is equal to 0.1. Similarly, x2 is 0.2 and so on. The value of y at x0 is denoted by y0, which is y of x0, which is y of 0, which is equal to 1 by the given initial condition. So we have to find y1, which is y of x1, that means y of 0.1, y of 0.2, that is y2, which is y of 0.2, and so on. And we have to continue to find y11, which is equal to y of 1.1, or the value of y at the point 1.1. So for n equal to 0, Euler's method gives us y1 equal to y0 plus h into f of x0 plus y0. So y0 plus h into f of x0 y0 value is x0 plus y0, because you know f of xy is x plus y, so f of x0 y0 is x0 plus y0. Now we substitute the values. Y0 is 1 plus h is 0.1 whole into x0 is 0 plus y0 is 1. So finally we obtain the value of y1, which is 1.1, means y at 0.1. Similarly, we calculate y2 using y1 x1, which is 1.22. In this way we continue to obtain y at 1.1, which is 3.60. So no given option is correct. There is a typo in the question. Either we have to find y value at 0.1 instead of y at 1.1, or the initial condition is y of 1 equal to 0 instead of y of 0 equal to 1. So with the given data, if we have to calculate y of 0.1, then it is 1.1. You can see here using Euler's method. Otherwise, if we change the initial condition y of 1 equal to 0, then the value of y at 1.1 using the data by Euler's method, we obtain the value of y at 1.1 as 0.1.